Properties of air. Air is often taken for granted since it's always here in the lower levels of our atmosphere, which is called the troposphere. You do not feel air since the air inside and outside of your body is at the same pressure. Probably the only time air is really noticed is if there isn't any in the room where you are, and there's nothing to breathe. As you start to turn blue and pass out, you're probably thinking about air. As we begin our studies of aeronautics, it is very important that we understand the properties of air and how they affect the properties of lift of an airfoil. For example, if we were to study how much airspeed or length of runway it will take different airplanes to take off, we can see how the properties of air will affect the performance of an airplane. The first airplane is taking off from LaGuardia Airport in New York City, which has an altitude of 20 feet. It is a cold winter day with low humidity. The second airplane is taking off from Denver, Colorado, which has an elevation of 5,430 feet on a hot summer day with high humidity. The plane taking off from New York will require much less airspeed and runway length to take off. Why is this? If we were to take a really close look at 1 cubic foot of air, we will see that the air is made up of very small particles called molecules. These molecules are rather far apart in relation to each other and are in random motion bouncing off of each other and the walls of the container. The movement of these molecules will be affected by temperature, volume, pressure, and moisture content, humidity. This is why we can state that air has the following properties. Air has density, or mass. Air has volume. Air is under pressure. Air has temperature. Before we begin to take a look at these properties, let's take a look at the term called standard day air. Due to the fact that air is affected by all of these conditions, we need to have a standard to measure or compare air, a sort of starting base point. This will allow a pilot to have something to reference when trying to figure out how much runway it will take for his plane to take off. Standard day air. Elevation. Sea level, or 0 feet of elevation. Density. Rho. 1.225 kilogram per meter cubed metric, or 0.00237 slugs per cubic foot English. Pressure, P. 1013.25 hectopascals metric, or 14.7 pounds per square inch English. Temperature, T. 15 degrees centigrade metric, or 59 degrees Fahrenheit English. Air has density. The density of air will be in almost all aeronautical formulas and is referred to as rho. As altitude increases, the density decreases. This is caused by there being less molecules of air and the molecules being further apart at altitude. Let's compare two different 1 cubic meter containers of air, one at sea level, the other at 10,000 foot elevation. Formula for density. Density equals mass over volume. D equals m over v. The density of an object can be defined as how many molecules are in a cubic meter. As altitude increases, the density decreases. This is caused by there being less molecules of air and the molecules being further apart at altitude. If we compare 1 cubic meter of air at sea level, where the air density is 1.196, to the density of air at 7,500 meters of 0.451, we can see why we need outside oxygen to breathe at the higher altitude. At sea level, the air molecules are tightly packed together and as we go up in altitude, they get further apart. This means we can actually measure the amount of air in a container by measuring the mass, or the weight of the container. For some experiments on this, let's head out to the MechNet Aeronautical Research Facility and see what sort of experiments Professor Kokins has for us.
Hello everybody, and welcome to the MechNet Aerodynamics Lab. Today we're going to be investigating the 4 properties of air. Air has mass, air has volume, air has pressure, and air is affected by temperature. The first one of these we're going to take a look at is the fact that air has mass or weight. We don't really think about air having any of these properties because of the fact that it's always around us and always there. But as we can see, what we've done here to illustrate this is we have 2 different plexiglass cylinders mounted on this balance beam that both have the identical amount of air inside of each. That's the reason that both of them are balanced out perfectly. Now, what's going to happen in this experiment is the cylinder here on the left we have connected to a vacuum pump. When I start the vacuum pump, what we're going to do is suck the air out of that cylinder. And as we suck the air out, let's take a look at what happens. Okay, as we can see, the cylinder over here raised up. As we remove the air, we remove the weight or the mass out of the cylinder. So now what we're going to do is shut off our vacuum pump and allow air back in the cylinder. As we allow air back into the cylinder, let's see what happens. And as we can see, as we let the air back into the cylinder now went down again.
Temperature, pressure, and volume. All 3 of these properties of air will affect each other. As any one of these change, it will affect the other 2. This can be stated with the formula P1 V1 over T1 equals P2 V2 over T2. We can see by this formula that by changing the initial pressure, temperature, or volume, we will change the final temperature, pressure, and volume. Now let's take a look at these individually to get a better understanding how they react to each other. Temperature. The temperature of the air will change the speed of the motion of the molecules. When we measure the temperature of the air, we are actually measuring the mean kinetic energy of the gas. The molecules in the air are always in a constant random motion, and there is energy connected with that motion. The higher the temperature, the greater or faster the motion. Thus, increasing the temperature will increase either the pressure or volume of air. Pressure. 1 cubic foot of air at standard pressure weighs 0.07651 pounds, or 37.7 grams per cubic foot. Standard atmospheric pressure at sea level equals 14.7 psi, pounds per square inch. Atmospheric pressure may be measured in many different units. A more common measurement is inches of mercury. This is the term you hear when the weatherman gives the barometric pressure for the day. The unit, inches of mercury, is based on the findings of a 17th century physicist, Torricelli. Mercury weighs 0.491 pounds per cubic inch. At standard conditions, standard day air pressure will raise a column of mercury 29.92 inches. When a high or low pressure system exists, the barometric pressure will rise or lower accordingly. Wind flows from high pressure to low pressure. In aeronautics, we often use inches of water to express pressure because it is more sensitive. The same pressure will cause a greater rise in a water column than in a mercury column. The specific gravity of mercury is 13.6. Its density is 13.6 times that of water. As you can see, standard air pressure pushing down will raise a column of mercury 29.92 inches and a column of water 406.88 inches. Here is a comparison between inches of water and inches of mercury. Volume. Air will take the shape of the container it is in. How about if we see what Professor Kokens has for pressure and volume?
We don't often think of air having pressure because of the fact that the air inside of our bodies and the air outside of our bodies is at the same pressure. So we don't really feel the fact that there is actually 14.7 psi of air pressure on us right now. In fact, the way this happens is we just proved in our last experiment that air has mass. Well, we've got all that mass on us. From the top of the troposphere all the way down, that's where the air pressure comes from. If anyone ever states they feel like they have the weight of the world on their shoulders, it's pretty close. You got the weight of the entire troposphere on your shoulders. Anyways, for this experiment here, we've got a simple balloon inside of a vacuum jar. What we're going to do, when we turn on the vacuum pump, we're going to suck the air out of the bell jar, and let's see what happens to the balloon when we do that. Action. Okay, what we can see here is that the balloon expanded to the size of the bell jar. Actually, that's another sort of property of air, is air will take the shape of the container it's in. The balloon has expanded because of the fact that we lowered the air pressure in the balloon expanded out because of the lack of air pressure. Okay, what we've done here is we've put a smaller water balloon in our bell jar, and we'll apply a vacuum to it. And let's see what happens to the water balloon. Oops, I think we need a bigger balloon.